Hello, everyone. Thank you for attending today's webinar titled Flexible Automated Cutting Edge Material Handling, brought to you by Products Finishing and presented by Therma-Tron-X. I'm your moderator, Scott Francis, editor of Products Finishing. Today's presentation will last about 40 minutes and will cover new innovations in material handling for finishing operations and considerations that should be taken into account when exploring solutions. A question and answer session will follow the presentation. If you have a question, you can type it at any time during the webinar in the question field of your GoToWebinar control panel. This webinar is being recorded and when complete will be made available to you via email from Products Finishing. Our presenter today is Joe Lobenthal, Sales Engineer for Therma-Tron-X Incorporated. Joe joined TTX in January of 2015. His background as a technical sales professional at global corporations has gained him significant experience in the application, design, manufacture, and operation of industrial paint systems. Joe has served as president and as a board member of the Northern Illinois chapter of CCAI and as a committee member of PCI, and is also a member of the National Association of Sales Professionals. Joe, with that, I'll hand it over to you.
Thank you, Scott. Hi, everyone. Good afternoon, and thank you for joining us today for this webinar. On behalf of everyone at TTX, we'd like to thank you for taking time out of your day to join us. I hope that you'll find the information that's presented to be informative, interesting, and relevant. And again, on behalf of TTX, thank you. Material handling considerations. I want to take just a step back and look at what are considered to be traditional material handling systems in finishing operations. So we'll talk briefly about continuous monorail type systems, power and free systems, some of our square transfer indexing systems, programmed hoists. So a lot of the types of systems that have been used for many years for material handling in painting and finishing operations. And then we'll get into some of the new innovations in material handling as well. So just briefly to talk about continuous moving systems. Many of you are probably familiar with overhead conveyor systems, whether they be a continuous moving monorail with a chain, or perhaps power and free conveyor systems, where product is typically suspended from carriers or from pendants and moving at constant speed throughout the finishing operation. And again, these have been used for many years for a wide variety of applications and reasons. We see them throughout the industry. Very robust designs and have held up well over the years. We get into more continuous systems. Some of the benefits, obviously, very high volumes that can be run on some of these overhead conveyor lines that are running continuously, high volume capability and production rates, a lot of flexibility for process design times. They can run at variable speeds throughout the process. With continuous monorail systems, it's nonstop throughout the entire process. The systems can be designed to accommodate part sizes of almost any shape and size and configuration. So a lot of flexibility in terms of system design and system approach. Monorail systems, however, offer very little flexibility for multiple process sequences. So if you have perhaps multiple paint booths or quick color change applications where you want to move in and out of colors frequently throughout the day, monorail systems are limited in what they can provide in terms of that flexibility. Also for loading and unloading product, not the ability to stop or to queue at load and unload stations to load and unload product to and from the conveyor systems. So not as flexible as other types of conveyor systems. However, a traditional monorail system is probably your lowest cost option when looking at material handling for basic finishing operations. Power and free conveyor systems, where you still have the monorail system supporting the load, then a continuous operating chain running along with that above it provides more flexibility in that you can now stop and start at select areas in the process for painting or loading or unloading, for queuing, for perhaps assembly. The conveyor systems, the power and free systems are often routed out into the plant, into weld cells or assembly areas after paint and finishing. So they do provide some flexibility. Along with that flexibility comes significant additional cost and preventative maintenance, as you have considerable amount of conveyor chain associated with the power and free system that's routed throughout the plant to offer you the ability to switch and to move from track to track in a power and free system layout. Square transfer indexing systems are used throughout the finishing process. This clip that you're seeing is a square transfer system at Oshkosh Finishing Services. So the advantages of square transfer or vertical lift systems is now I can do a lot in very little space. In this example, you're seeing a pre-treatment and e-coat process where the tank sizes are sized just big enough for the part package themselves. So take volume can be reduced significantly over traditional monorail or power and free systems. Also gives you the ability to route these part packages through assembly areas and elsewhere for queuing, for assembly, for welding, in a very small footprint in the plant also. So again, some parts can be stationary for painting processes and move from point to point in the process with square transfer as well as power and free. Part envelope sizes can be adjusted so you can rack very densely going through an immersion process for pre-treatment cleaning and possibly e-coat. But where you want to top coat after that, we can separate the parts on these dense racked part packages and separate them into packages that are appropriately sized for top coating. Again, great part density, great production rates out of square transfer systems as well. Very flexible in that we can process bulk materials in racks, baskets, and barrels, primarily for e-coat, pre-treatment and e-coat as well. So some flexibility in terms of design and approach with square transfer indexing systems, all while minimizing the footprint in the plant. Vertical product entry and exit, meaning that we can lift from the pre-treatment cleaning sequence to directly above to ovens that could be mounted overhead, again, to conserve space in the plant, and very efficient oven designs also. Programmed hoist systems, much like the indexing square transfer systems, where we can provide pre-treatment, cleaning, electrocoat in a hoist configuration. So very large part packages where we can tilt product in the tanks and above the tanks for drainage. We can send product from the painting and pre-treatment process off to assembly areas, secondary operations such as sealant application, primer and top coat as well, in a much smaller footprint than we might otherwise do with traditional monorail or power and free systems. Again, program hoist systems have been around for many years. They provide a lot of flexibility. Cycle times can change. Immersion times can be different from tank to tank. Load bars are moving vertically and horizontally. So again, very little footprint, minimizing the footprint in the plant, which is so important to all of us today as we're planning our new coating processes. Again, densely racked or very large parts, the ability once again to separate these into part packages that would be appropriately sized for top coat applications, and the ability obviously to send these part packages off to secondary processes such as assembly or additional coating. A lot of flexibility in design times here too. I can have different dwell times at different stations throughout the layout, from pre-treatment through coating to painting, top coating, assembly, and into the weld cells as well. Again, small footprints, very focused on trying to minimize plant floor space these days in many of our designs. So that's just a brief overview of a lot of the conveyor systems that have been used for many years, and they all offer advantages, one versus the other. But as we go forward, we're looking at, different ways to approach this. We spend a lot of time today looking beyond the paint operation or the finishing process itself. How are the materials being brought to the finishing line, and where do they go after? So rather than focusing just on material handling in the finishing process itself, we want to consider material handling throughout the plant, and how can we integrate that with our finishing process to reduce forklift traffic, to reduce the opportunities for errors in transporting product from point to point, safety as well, minimizing forklift traffic and people pushing carts around or moving product throughout. So TTX has come up with the Automated Conveyor Carrier System, or ACC, a safe, flexible, cost-effective material handling solution for finishing and manufacturing and assembly operations. So what is an ACC? It's an autonomous traction wheel driven conveyor carrier guided by a single overhead I-beam conveyor rail. So the ACC was really a cousin to the automated guided carts or automated guided vehicles that many of you may have in your plants today. And we've taken that same concept and integrated it into an overhead conveyor carrier. So the technology that we're using is robust. It's been well proven for many years in terms of laying out the mapping in your plant and how we go point to point in our process. So again, taking some existing technology and adjusting it and using it to meet the needs of the markets today. Obviously, as we're designing any systems at TTX, our objectives are safety, sustainability. We want to be very flexible in our approach and design systems that are easy to maintain and operate. Excuse me, the ACC carriers, I'm going to take it. When we talk about safety, each carrier is self-driven. So we have torque control on each individual carrier. And this can be adjusted carrier to carrier to account for different weights or different elements in the process, different places in the process where greater torque might be required versus other areas in the process. It also allows us to design the carrier to pull the load only, just enough torque to move that load from point to point, which is really great in terms of safety. Blue safety lights, the beacons that many of you are familiar with on your forklifts, are installed as in basic configurations. As these are running around overhead in your process, they're very quiet, so they can't sneak up on you. So safety lights or scanners or laser bumpers can be integrated as well. Audible alerts also letting you know that they're coming. So a lot of ways to allow individuals in the plant to understand that you have moving carriers above you, moving product from point to point. Because unlike traditional conveyor systems, these are very quiet, operate very quietly. So it's very important to understand where they're at and how they're moving from point to point. A little bit more about safety. Again, a quiet and clean operation. There's no chain in this system. The chain that's used in all of the traditional systems we talked about, and the drives associated with that chain, and the rattle of trolleys and carriers that are in power and free systems that are engaging and disengaging. All of that is eliminated in an ACC system. And unlike electrified monorail systems, we have a totally enclosed power source. There's no exposed conductor bar. So there's no electrical bus running along the length of the rail. like a street trolley or again, an electrified monorail where I'm coming into contact with that bus to power the carrier. So very safe and clean. These are battery operated systems using lithium ion, or probably more popular is the absorbent traditional glass mat batteries in each of the individual carriers. Sustainable, okay. Using a system like this allows us to build systems in a modular form. They're easy to expand as your systems need, your requirements need to grow and expand. They're scalable. We can design a system and provide just the number of ACC carriers that are required to meet existing needs while easily accommodating growth in production rates and extension out into other areas of your plant at later dates simply by adding more carriers and more track. Energy efficient. Because the carriers will be located outside of ovens, we're not passing the carrier through the oven like a traditional conveyor chain. They are located above the ovens. So the oven volumes are reduced dramatically from traditional ovens. It has less oven volume to recirculate air in, really designed to accommodate your part package only. I'm also not bringing in all that chain and carrier mass that you do with traditional conveyor systems that I have to heat up constantly along with the parts that I'm drying off or curing in the ovens. So much of that metal mass is outside of the oven now. So we've reduced that mass flow significantly, requiring smaller burners, smaller recirculation fans, lower cost and lower energy. Processes can run only when the part is present. So they can be integrated with your control system to ramp process equipment up and down if that's appropriate in your process. Easy to do. And again, these are autonomous. So zone and carrier control is independent with each carrier. Stopping and starting independently. They're not beholden to chains or carriers, predefined centers on chains in traditional power and free conveyor systems. So again, a lot of flexibility in terms of approach and design. Sustainable floor space. Again, we can nest these systems into very little floor space, and we could take advantage of future growth and expansion by simply routing conveyor into future space, future state planning. In the photograph that you see, that is simply the contact point. So when we look at the downtime and carrier maintenance, I have opportunity battery charging. So throughout your conveyor system, there'll be battery charging points. So I'm not pulling carriers offline to recharge these batteries. Oftentimes in a layout, you'll have queue or buffer areas or cooling areas, or even above the oven where you might be standing still for some number of minutes. In those select areas of your layout, we can put a charging station to charge these batteries in process. So I'm not moving anything offline to maintain these systems. Again, on floor space, we've eliminated so many of the chain routes, or all of the chain routes actually. So tons of flexibility in design here. Resource efficient. So each carrier can travel, accelerate, decelerate, and move in any direction independently. For example, if I'm carrying very heavy loads from point to point, I can accelerate slowly and then move to a quicker speed if I'm just moving from point to point. I could then slow down as I approach my destination and come to a stop, unlike traditional material handling systems where I'm traveling at transport speeds of maybe 40 to 50 feet per minute and then coming to stops. So there's a lot of engagement between the carriers from point to point, making a lot of noise and a lot of wear and tear. I don't need a lot of empty hooks to keep my line running. If I don't have parts to hang, the carrier is going to wait until hanging my parts or unloading my parts. I don't have that constant line moving. I don't have production gaps by design anyway that I have to concern myself with. Recipe control is certainly a part of the system, allowing you to create recipes for destinations where you want to send the carriers, the information that you're carrying along with the carrier. So paint information can be routed along with the carrier, sending it to the correct paint booth. Along with that, the information that's passed off to the application, the paint or powder application equipment, is routed along with that for adjustment from carrier to carrier for your paint application. So recipes for destinations from point to point within the conveyor system itself. How do I get from point A to point B? What speeds do I operate at during my routing? That's all designed into the individual carrier as it's moving from point to point. Can be integrated obviously with ERP, your SAP systems or other ERP systems that you're operating, so that we can collect data along the way. Data such as oven temperatures, pre-treatment information, things like that that might be important to your quality groups to understand the parameters that were in place as you were processing your materials. That's all easily integrated into the system as well. Point of use reduction in material handling. Again, we can try to eliminate a lot of forklift traffic by using both ACC overhead carriers and AGCs, the AGC carts along the floor, automating that process as well. We make every effort to try to reduce forklift material handling throughout not only your finishing process, but your welding and assembly processes before and after. The two can work together very well. So again, flexible, what you're seeing in that image is simply the conveyor layout for an ACC system. So it's a monorail. There's very little infrastructure required beyond the rail itself. It can be supported from the floor, supported from overhead, much like traditional systems, but it is just an overhead I-beam rail designed to support the load. And that's it. So you can imagine how easy it is to modify or expand your layout at any time. You're not dealing with conveyor change or external drive mechanisms. Those are all intrinsic to each individual carrier. So again, layout flexibility, expansion, modification, very easy to accommodate. Very creative too, unlike some of the traditional systems that are more like once they're in your plant, they're there forever. It's hard to move with all the chains and the drives and the infrastructure that's in place, these monument conveyor systems that we've seen for years. So we simply plot your course, to get from point to point, and how do I need to get there, and what am I taking to each location? Very simple to lay these systems out. You can be very creative. We can shuttle, we can do lateral transfer from point to point. Switches can be incorporated, much like traditional conveyor power and free systems, just without all the additional chain and infrastructure that goes with switches. We can do some other creative things too. We can put turntables or intersections, just like a four-way stop in a system like this. So again, some of the flexibility here. Scalable, we've talked a lot about that. The system can grow as your demand grows. Easy to do and expand and modify. Again, considering a lot of what takes place beyond just the finishing or painting operation today. How can we integrate that easily into the process? Here's an example of a turntable, much like a turntable in an old roundhouse, if you will, for the trains. It's a four-way intersection that I can approach from any direction with an ACC carrier, and the turntable will route it to the correct destination based on the route map and the planning associated with that carrier. That's totally unlike anything we've been able to do with traditional power and free conveyors or monorail conveyors or even hoist systems and square transfer systems. So something unique to the ACC system. So when you look at floor space in your plant and the flexibility to locate your equipment within the plant offers some real advantages over traditional systems. Can be integrated easily with your blasting operations, fabrication and load systems, pretreatment ovens, paint, unloading and assembly. Lift stations are easily incorporated into this design as well. So with traditional power and free conveyor systems, lift stations have always been an option. But when you're lifting, you've got to reroute the chain around the lift station. You've got to push carriers in and out of the lift station. There's a lot of infrastructure associated with that lift station. With an ACC carrier, we can simply lift the rail section that the carrier is sitting on, and that's it. So I'm still putting a lift mechanism in place. All I'm lifting now is the load rail itself and the carrier with the weight suspended from the carrier. So much easier to design and integrate lift stations at lower costs. It can be used in immersion, pre-treatment, and cleaning processes. We're very precise and accurate with locating the carriers along your route as well. The encoder that we use is absolute position encoder. So I can literally stop these carriers on a dime. My engineers will tell me that it's even more accurate than that. But when you think of robotics used today in many of our operations, both for loading and unloading, for paint application, sealant dispensing, the precise and repeatable location of that part package is so important. Hard to do with traditional conveyor systems on a routine basis. Our ACC system allows us to stop precisely at the point required to present that part package to the robots for application, for loading, for unloading, making that a much more robust process than would have been possible with traditional conveyor systems. Traction control. So what we're able to do with traction control is simply increase the tension on the drive wheel over select areas of the system. In a very simple way to do that, for example, is that if I'm going over a blast unit, an inline blast system, I may want a little more traction on the drive wheel because the hangers going down through the slot of the blast system may encounter more resistance, okay? So my carrier is designed just to move the load, nothing more. So if I do run into an obstruction along the way, my carrier is going to stop much quicker and much safer than it would otherwise in a power-free or traditional monorail conveyor system. If you've had the unfortunate experience of seeing your conveyor engage with a forklift or a part rack or something, trying to get that conveyor to stop properly before damage is done or somebody is hurt is so important. The ACC carriers will stop with very little resistance under normal use, but I can increase that resistance over select areas of the process just by modifying the rail slightly, or we can integrate a tensioning device on the drive wheel as well to do that automatically. But it's done very simply mechanically too, to increase the tension to drive through the seals on a blast unit where I get a little more drag perhaps than I would through a paint booth or through the oven. And when we think of maintaining and operating a system like this, so if I have 3 or 4 miles of conveyor in my plant and it's power and free conveyor systems, and you've had that experience, you know that there's a lot of maintenance associated with those systems. And again, they still might be the right fit for some applications today, no doubt about it. But with the ACC system, there's far less maintenance required on that infrastructure. I have no lubricators in this process. So I'm not maintaining lubes, I'm not lube systems. I'm not cleaning up lube. I'm not worried about a lubricant or dirt or contaminant dropping onto my parts. I'm not spending money on that consumable. No chains to clean or trolleys to clean in the process as well. So again, just eliminating a lot of the maintenance items that are associated with traditional conveyor systems. There's very little electric and pneumatic infrastructure associated with the ACC conveyor layout. We have your I-beam rail that's supporting your load. Beyond that, there's some pneumatic or electrical infrastructure to throw switches at turns or to rotate turntables. But I don't have stops. I don't have things like that I would in traditional power and free conveyor systems that are constantly opening and closing to stop my carriers along the route. None of that is required with this system. So we've reduced significantly the electrical and pneumatic infrastructure associated with traditional power and free systems and other types of systems as well that are used today in these operations. Maintenance spurs could be added anywhere in the system very easily. If you want to pull a carrier offline for regular routine maintenance, that's easily done by adding a spur and a switch and adjusting your route map. So easy to do, easy to integrate at most places. Carrier maintenance as well, and a maintenance spur. So as you can see in the photograph, this is a very large ACC. It's a 30-foot long carrier supporting up to a 6,000-pound load. These systems can be designed to accommodate very small part packages as well for more traditional load sizes that might be several thousand pounds or 1,000 pounds. A lot of flexibility. This is a multi-carrier that you're seeing here with the drive carrier at the front and a slave carrier in the back, and then your big load bar suspended from those two, supporting a much heavier load weight. But they can be designed to accommodate more traditional sizes as well. Easier to remove and replace these carriers. Again, I'm not dealing with all the chain and all the infrastructure associated with traditional conveyor systems. Each of the ACC drive systems, that module is the same for each module or each carrier on your system. All the component parts are the same from carrier to carrier. The replacement parts, the parts that the carrier is built from are all configured with parts that are readily available from suppliers. There's really nothing proprietary in the build of the system, the components that are used in your carrier. So stock replacement parts are easy to find, easy to replace, whether you get them from TTX or from a local source. It's important to us that you can maintain and operate your system easily. Again, we're taking technology that has existed for many years in the automated guided vehicle and cart industry, cousins to our own ACC carrier, and integrating that with this ACC design. Easy modification, we've talked a lot about that, but it's really a big emphasis put on that in terms of flexibility here. The operation of the unit, we're using a wireless Ethernet network, a map, if you will, of your entire material handling process. So we understand exactly what this process looks like, point-to-point movement on the process. We're transmitting information to and from the carriers through the internet, Ethernet network. The linear encoder and sensor is provided on each carrier for precise positioning and also feedback to the control system. So we know exactly where that carrier is at in your route, where it's heading to, where it's come from. So we've got entire traceability throughout the system from carrier to carrier, precisely located. Again, as I mentioned earlier, with the linear encoder here, we know exactly where each carrier is and able to change routes in process as well, easily done if we need to. If you defined a destination when you loaded the carrier at your load cells, and for some reason you need to redirect it to a different booth or paint system, that can be done in process as well. So as long as we define that route map up front, including your decision points, your different points in the process, painting, pre-treatment, loading, unloading, all those are mapped out. All your decision points are well defined. Then we're simply routing these carriers from point to point and tracking them along the way. A couple of videos that you'll see here. These were some of the testing that was done at TTX several years ago as we proved these systems out. We spent 24/7 operation in our plant prior to going into production. You can see the linear encoder tracking an encoder tape that's mounted to the rail that presides very precise positioning of the carrier along the path. And if for some reason that encoder tape is damaged or skips or is missing for a short length, just like the automated guided carts, the carriers can have the ability to go past that up to a certain distance and continue to move without stopping. Where there are some fail safes we want to design into the system as well to keep it from going beyond a certain point. But if there is some tape missing for any reason, if it's damaged for some reason, the carriers can move past that without stopping. So forward and reversing as well. The video that you see on the right, you can see acceleration and deceleration in process of the carrier speed. And as I approach turns, I can slow down, I can reverse, and I promise you I'm not just reversing that video. The carrier actually is reversing and moving the opposite direction. So it's very easily done. We can accommodate that. You can imagine a J-spur where I maybe went around that 90-degree turn, stopped, and then a switch was flipped, and I proceeded straight the other direction. So again, so much flexibility here. And we're supporting very heavy loads in these carriers that you see in these images. And again, you see the drive unit in the front. That's about a 6-foot pin to pin, 6 to 7 feet from pin to pin of the trolleys on that front carrier. That could support a load in and of itself, up to several thousand pounds also. Doesn't necessarily have to be designed to be as large a carrier system as you see in these images, but easy to incorporate for smaller part packages as well. Again, the Ethernet sending and receiving data to each individual carrier. Our destination, our routing, reporting, special functions, all this is real time throughout the process. So you're sending and receiving information, you're collecting data if that's what you need, that's what's required. So battery levels, all the operational parameters associated with each individual carrier we're monitoring real time. The opportunity battery charging stations throughout the system to keep us from having to come offline for battery charging. The systems are designed so that the battery does not exceed about 35% the depth of discharge on the battery. We stay about 65% charged on each of the batteries. And that's where it's kind of the sweet spot, if you will, where the carriers work best, where we can charge them at the right intervals and continue to operate nonstop. So you're not pulling anything offline for carrier charging, battery charging, or maintenance. We can obviously integrate these with a lot of different equipment configurations and processes. We can do simulations depicting how these systems would work in production to ensure that you're getting from point to point to minimize any opportunities for backups or delays or and continue to expand rather than the paint operation that you see in the center of this image. You've got welding and fab on one side and assembly on the other. It can also allow us to be very creative in our design and approach to our finishing processes. For immersion pretreatment systems, an example you see here, I can move carriers forward and reverse in and out of pretreatment processes into oven systems. Again, a lot of flexibility, even within the pretreatment process, lateral transfers using ACC carriers now versus traditional methods. Very easy to integrate, very efficient. Again, on behalf of everyone at TTX, I want to thank you for taking time today to join us for this webinar. If you have any questions, please, now is the time. So go ahead and send them to us and we'll be happy to take what we can. And if you want to contact me personally, here's my contact information as well. So thank you again from everybody at TTX.
Thanks a lot, Joe. Now that it's the question portion of the webinar, please use the question field on your GoToWebinar control panel to submit questions. And as a reminder, the webinar is being recorded and when complete will be made available to you via email from Products Finishing. So first question, how long do the batteries last?
Oh, okay. Good question, and that's one we'll often be asked. So if we are speaking towards life expectancy, the AGM or acid glass mat batteries that we use are identical to those used in typical AGV and forklift fleets. And the good news is that our runtime characteristics for the ACC tend to extend battery life when we compare that to, the AGVs and the forklifts. We base this on charging cycles, which is dependent on a lot of characteristics, such as the loads, the charging stations, runtime, idle time. So there's a lot of variables that go into that. However, based on test runs at TTX, we've established that a set of batteries have readily exceeded 3 years of service during that test that emulated a 3-shift operation under full load. So short answer to a long answer, we're saying at least 3 years of 24/7 sort of operation. And we are still collecting data on that as the first systems are out in production today as well. When we think of the travel distance, again, the range is, again, we want to keep powering these up in process to keep them in that sweet spot of charge where the batteries are about 65% charged. And there's benefits for that rather than having them fully charged or drop below that. Probably not unlike a lot of our iPhones and phones that we're using today. There is that sweet spot. So that's important to us that we map that out properly and keep those charging stations appropriately designed.
So with that said, what is the cost of a replacement battery?
Well, I guess depending on the size of type, but typically the acid glass mat type of batteries that we use, a typical list price is probably around in that $900 range. But then you look at that over the life of the system, and it's very little in terms of replacement cost.
So for ovens, does the drive unit remain outside of the oven with a slot seal?
Yes, it does. So we have a slot seal on the top of the ovens, and we find we get no heat escaping out of the slot seal on our oven design. So we're not exposing that carrier system to heat. It's outside of the washer as well, outside of the paint booths. So we're not exposing that ACC carrier to any of the processes down below. So yeah, oven designs with slot tops with a unique TTX seal at the top of the oven have been very successful in keeping the heat in the oven, keeping it out of the plant, and any exposure to the ACC system at all.
So how do the carriers keep from colliding with each other?
Well, I talked a bit about the encoders that are on each carrier. So we're tracking those point to point in the process. So our control system can calculate the distance between the carriers, and if or when necessary, we can take action to prevent any sort of interference. So by design, they're not going to run into each other. And if there is, for some reason, the carriers are designed in such a way that they would stop together, much like a traditional power and free carrier would stop, or they would nest together where you don't have any sort of damage being done to the carrier or to the load below. But the control systems are very robust, and because we're tracking each of these carriers individually throughout the process, that sort of interruption just should not occur.
How do you determine the tension required for the drive wheel tensioner spring?
Wow, somebody's listening here. Okay, the drive wheel is adjustable. The traction, the amount of traction is adjustable. We want to keep the system as safe as possible, so we set that traction really only slightly above the needs of the system. And I talked a little bit about that. So there's just enough traction to move the load from point to point. That way, if we do engage an obstruction, the carrier is going to stop. It's not going to drive through anything. We've got to consider the weight of the load, turns, process requirements. And so we've got set points that we'll start each carrier at, and then they're easily adjusted in the field to meet the specific demands of the environment that they're working in. And we could set the traction device at its maximum setting, if you will, and it still won't exceed the drive rating on the motor itself. So I can't over torque it.
Cool. Well, I think that does it for our questions. And we've come to the end of the webinar. So thanks so much, Joe. We really appreciate your time today and your presentation. I'd like to say thanks to our attendees for taking the time to join us today as well. We really appreciate you being here and hope you'll join us again for the next products finishing webinar. For more information, please visit pfonline.com/webinars and have a great day, everyone.